Rough as Guts Videos returns to your screen with the last installment of the exciting saga of C pointers. At least this is the last in this particular chapter. Pointers will continue in subsequent chapters. So this one is about array parameters. I'd like to recap what we did a little bit in the last video where I introduced an array of numbers. I set up a pointer which was initialized to null, then I assigned it to point to the first element in the array, and I printed both the pointer that I had created in that way and I passed in the array apparently variable itself. And what I got, as you can recall no doubt, is the same answer for both, and the reason, which hopefully you can also recall, was that nums is essentially the pointer to the base of that array. This is a function, printf. I just passed in an array to it. The same rules apply if I declare my own function. So let's have an integer function max, which is given a count of the number of elements in an array, and then it's given the actual array, which we'll call data here, and it's going to go through and find the maximum element in that particular data, which it does by doing something like int big is the 0th element, and then it looks at all the rest in turn with an index which starts at 1, and as long as that's less than the given n, incrementing each time through, it checks to see if the element at that location, data of I, is greater than big, and if so, it updates big accordingly. And at the end of all that, it returns the value that it's just found for big. If we check that works, we'd better have a call to it, so we'd better go printf biggest is equal to, can't spell, biggest is equal to %d new line, the maximum of the 3 elements of the variable array nums. Let's try that. It compiles and it prints that the biggest is 30, which is a good answer given the numbers 10, 20, 30. As I said a minute ago, when you pass in a parameter, an array as a parameter or as an argument to a function, the actual parameter, the type of it, although it appears to be declared as int data open close brackets, it's actually an int star. So what we're actually receiving here is a pointer. I'm going to write the code a little bit differently to make the clear. Well, first of all, no, I'll do two things. I'll do that first and prove that that compiles. It's a little bit confusing because int star data somehow or other doesn't capture the essence of the pointerness nature of the variable. So I'm going to write the code a little bit differently using the term pdata. And because it's a pointer, I'm going to switch to a version of code that makes that clear. So short pause while I do some fiddling. So after the fiddling is complete, here's our modified version, which uses the explicit pointer iteration approach. So we set up a pointer that points to the last element of the array, or actually the one past the last element of the array. So this is off the end of it, which always struck me as a trifle odd first time I saw it, but you get used to it. It's just an address, after all, an address just off the end of the array. And as long as the pointer that we're working with is less than that, we step through the array, picking up, checking each element in turn to see if it's greater than big. And if it is, we reset big. Notice one thing here. Int big equals star pdata plus plus is another C idiom. It says fetch the element pointed to by pdata. That's why we're going indirect through it, and then increment the pointer afterwards. So after that statement's executed, pdata is pointing at the first element, and then continue through the array until as long as we're inside the range of the array. So that's what this slide here was showing. There's no real benefit in using the pointer version of it over using an indexed array, and I encourage, in fact, using an indexed array. It's easier for most people to read. But a lot of C programmers, given a pointer, sort of feel they should stick with pointers. Notice again, I've called the variable pdata. It's really the same as the variable data, and you can experiment yourself if you like, replacing that with the word data everywhere. Nothing will change, or it should change. The next thing I want to introduce is a new type qualifier, as it's called, const. Short pause while I back up in the code. Here's the original version of code that I had using a data array declaration and indexing into the array. So this new type qualifier lets me specify that the array that I'm dealing with is const. So this still compiles. Let me just prove that and run it. The key thing that's happened here is that I've said explicitly, I promise in this function not to modify the data you gave me. This is kind of reassuring for this function that thought it was simply going to be told the biggest element of the array. So it's considered good manners, if you like, or good style to be explicit about facts like this in order that the caller doesn't have to wonder whether their array is going to be smashed. Notice if the callee tries to smash it by saying data of 0 is equal to 5, say, we get an error message saying, whoops-a-daisy, you said that was going to be const, read-only if you like, and now you've gone and tried to modify it. It even tells you, note, that it says the read-only location star data, because that's what data 0 is. It's actually going through that pointer. Again, you've just got to get used to pointers in C. So I can't do that. Given that, it's probably not too much of a surprise to you to know that if I switch to the pointer-based version of the declaration, I write int star data like that, that again, this is exactly the same. I've now locked down the array data. Now notice this is a little bit confusing. I haven't locked the pointer. The pointer can be varied. It's a pointer and I can do stuff with it. I can here say data plus equal 3. It's not very useful, not very finished with using it, but I can say that, and the compiler is happy to compile it and run it. It didn't change the output because I didn't go and change data till I'd finished with it. But the const doesn't relate to the data, it relates to what it points to. I'm going to switch to the pointer version of the code and show you something else now. So here I am with the pointer version of the code, and if I put a const in here, you'd think, well, surely that's exactly the same. But maybe not. Compile error. Warning, initialization discards const qualifier from pointer target. So this thing is the target of the assignment, and the initialization of it, it was set to be the address of pdata of n. Now, this is kind of subtle, but by doing that, I've essentially opened a loophole in the security, because now I could assign indirectly through end of data and mangle the data array via this pointer. And I haven't said it was const. So I'm being warned that I'm being inconsistent here. I said I wasn't going to modify the data, and now I've got a non-const pointer pointing into it. So I can solve that problem just by going const like so. Run that, and now it's happy and all runs again. So that's all I had for this particular video. The key takeaways are really that when I call a function, either a built-in like printf or one of my own, and I pass in an array, I'm actually passing in a pointer. The other thing that I brought into this was the notion of const, which is useful and strongly recommended for good style, that if you are given an array and you're not modifying it, you should be explicit about the fact in the type signature. That's all for this section of the notes. Thanks for watching. Bye.